All right, the last thing we want to do on introduction is actually get to physics. So we've talked a lot about science in general, some of the techniques we can use, but now we're going to actually say, what is it that we're going to be studying this year? So physics is, the best definition I like for it is a study of how the universe behaves. The big picture, what's actually going on. In some senses, we can think about it as a fundamental science. It's looking at all the pieces of things in the universe. What do they do? And to the best that we can tell, why do they do what they do? There's two major subdivisions in physics when you're studying it. There's classical physics, and this is basically everything that we as physicists established up to the early 1900s. This is what includes mechanics, which is how stuff moves. We're going to talk about that in quarter one and quarter two. And then also fluids and thermodynamics, which we're going to talk about for about half of quarter three. Whoops, and this has gone a little weird. It also includes electricity and magnetism, which will be kind of quarter three and quarter four. So all of that stuff is classical physics. It's stuff that was pretty well established and learned about up until like late 1800s, early 1900s. Then we have modern physics, which is everything that we've kind of discovered or built on or redefined after the 1900s. So this is all the stuff that is currently being studied. And this includes things like quantum mechanics, particle physics, relativity, aspects of cosmology, stuff like that. And the difference here is, the reason for the distinction is kind of everything in classical physics, classical mechanics, stuff like that. That was a building from about 1400, 1300, way, way, way back, just building and like better understanding the world, better understanding the world, better understanding the world, getting better and better, kind of refining, tweaking, adjusting, et cetera, and everything was building together. But then with modern physics, there were, if you remember way back when we talked about kind of laws and theories and stuff like that, modern physics is one of the best examples of there were things that fundamentally changed our understanding of the universe. There were some studies, particularly with quantum mechanics and special and general relativity, that said, oh, everything we've understood up to this point has flaws in it that are significant, and we need to completely rework what we've done. And that's why we have quote-unquote modern physics. Now, does that mean classical physics is wrong? I would say no. This is why we talked about models earlier. Classical physics is we can think about it as a simplified models. The math is typically a lot easier. The concepts are easier to kind of wrap your head around because they deal with the intuitive everyday understanding. And it works for all objects that are generally human-sized, meaning things that are the stuff we typically interact with, that are traveling at relatively low speeds, meaning they're not traveling near the speed of light. So your everyday experience is almost 100% perfectly described by classical physics. And the little slight off ability, the slight mistakes or amount that it's off by is completely not measurable. It's so small that it really doesn't matter. So I would say yes, classical physics is accurate, it's good science, it's useful because it's, compared to modern physics, a lot easier to use, and it helps us understand the world, and it, for all intents and purposes, describes things perfectly. Where it runs into problems is if you get to really, 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 really big things, like on the scale of galaxies, solar systems, universes, stuff like that, things you're not interacting with on a daily basis, things break. When you get really, really tiny, like atoms and smaller, things break. And when you get moving really, really fast, like near the speed of light, things break in classical physics. And so that's where start of the 20th century, people were thinking about that and were actually being able to start to do experiments on that and realizing, oh, our fundamental stuff, we have irrefutable evidence that says something needs to be different. And that's where we have modern physics. So that's why we're still studying classical physics. Out of all the classes I took in university for my degree in physics, probably 2, 3, maybe 4 or 5, probably about 3 or 4 classes out of the probably 10 that I took dealt with modern physics. The rest were almost exclusively classical physics. So it's still useful if you do engineering of like general mechanical engineering or general kind of everyday large structure engineering. Almost all the stuff you do is going to deal with classical physics. You will do modern physics if you're doing like electronics or some chemical stuff, but generally speaking, most of what everyone uses, if they're using any physics, is classical. It's just probably a third to a quarter of people that are focusing on specific things where those modern physics apply are using it. We'll still talk about both because it's good to be familiar with both, but I want to kind of emphasize this is what we're talking about with good science is something that helps you understand the world. So we don't throw out simplified models if they're still good science and still useful.